Welcome back as we continue our look at the endocrine system. This time around, we're going to take a look primarily at the thyroid gland and all parts of it, so both the thyroid hormone as well as parathyroid hormone production. So the thyroid gland itself is essentially our largest thyroid gland or endocrine gland that we have in terms of its total function. So thyroid gland is only dealing with endocrine functions. We have other organs that would be a little bit larger, but they're not strictly related to the endocrine system alone. So the thyroid gland, we've now moved away from the brain. So we're now down into the neck here. And in terms of the location, kind of sitting right in the front of the neck, right along with the thyroid cartilage of the trachea. I'm sorry, the larynx. And as it moves down there, it has two sides to it. So it has two lobes on either side. It's connected together as with an isthmus that connects the two sides that are there. When we look at the inside, when we look at here in a microscopic view in just a moment, we'll see that it has many numbers of follicles in it. Those follicles are filled with a substance called colloid, and this colloid is a combination of proteins called thyroglobulin and iodine. And so we have the ability to manufacture all of our thyroid hormone inside those actual follicles themselves. And so that's where the production of the hormone is going to occur. The cells that surrounded the follicle cells are essentially the ones that are bringing about the ability to have that combination occur inside the follicles themselves. In addition to the thyroid gland, sitting on the posterior side of that thyroid gland, we have the parathyroid glands as well. So those are on the end of the backside there, and we'll talk about those towards the end here today. In and around the thyroid gland and those follicles, we have the individual follicles, and it kind of almost looks like adipose tissue. In terms of microscopically, we've got these big open follicles similar to what you have in adipose tissue, except that now they're surrounded by many, many, many cells. And so we have all of those follicle cells that surround the individual thyroid gland itself. And then we also have parafollicular cells, kind of the cells that don't actually touch the follicle itself. And so those parafollicular cells are there as well, making up a bit of a smaller component to the thyroid gland that is there. So thyroid hormone is the goal of our thyroid gland here in terms of the major production of the hormones themselves. This is what's going to drive the majority of our metabolism in the body. It's going to essentially affect all of our cells and kind of turn up the metabolism of them when we do have our hormone. The hormone does come in two varieties, and so we have, with the hormone itself, we have T4 and we have T3, and this essentially comes down to how we put the molecule itself together. And so one of the major components of thyroid hormone is tyrosine. And so when we have tyrosine, we're going to combine that together with iodine, and with that T4, we end up having 2 tyrosine, and then we end up having 4 iodine bound to it. With triiodothyronine, we have 2 tyrosine again, and then we have 3 iodine combined to it. And so 2 different molecules of the hormone itself, as we'll learn a little bit later on, T3 being a little bit more biologically active than that of T4, but we can change that once we actually get to the tissues themselves. So thyroid hormone, it's all about metabolism. And so it's all about increasing our metabolism of the body. It's going to increase our glucose oxidation, so get the ability to utilize that glucose, make our ATP. Increase the metabolic rate, so if we've increased energy to the cell, we can increase what the cell actually has the ability to do. And we're going to have, in the process, heat production. And so heat is going to be a byproduct of all of that manufacturing process that's going on there. In addition to that, kind of, since it has an effect on things like the heart tissue as well, we're going to increase and maintain blood pressure at times. So if it's up or down in terms of the hormone itself, we may have issues that go along with blood pressure and cardiac function itself. It's going to be an important role, especially in developing tissue for tissue growth. So early on in development, as a embryo, as a fetus especially, that's going to play a big role. But then even after birth as well, so the two of them can have those components there. And very early on in life as well, this plays a big role in the development of the nervous system and the skeletal system. So if for some reason mom is thyroid deficient, the thyroid hormone does cross the placenta, so it can end up going from the baby into mom and cause some developmental problems on those as well. In addition, then, as we start to kind of mature and move along into puberty, we're going to go along with that maturation of the reproductive abilities that we have as well. And so it plays a big role in kind of the overall scheme of the entire body as things grow along. So this is all happening in those follicles. And so in order to get what we need to have in the follicles themselves, those follicle cells are going to produce thyroglobulin. So we're going to make this thyroglobulin, and then it's going to be essentially pushed into the colloid. So it's going to go into the follicle itself as well. So we need thyroglobulin, and then we're also going to need a bit of iodine. But iodine, when it is in a sense kind of floating around the bloodstream, it's as an iodide. So the first thing we're going to have to do is grab it out of the bloodstream. And so we're going to have to actively pump it into the follicle cell. So we're going to have active transport, taking that iodine and iodide molecules into the follicle cells themselves. And this process is what we call iodine trapping. Once the iodide is inside the follicle cell, we're going to take iodide plus, put the tails on there, plus iodide, and we're going to then oxidize it. And so we're going to have an enzyme peroxidase that is there, and this is then going to get us to our iodine. And our iodine is ready to go from the follicle cell into the follicle itself, into the colloid. And so iodine is going to make its way into the lumen of our follicle. And once it's inside there, now that iodine can start to bind to tyrosines that are on our thyroglobulin. And so we have, when one iodine attaches to a tyrosine, we get a T1. When two iodines attach to it, we get a T2. So we either have a monoiodotyrosine or a diiodotyrosine. And so now we can take T1s plus a T2, and that's going to get us a T3. Or we can then take two T2s and get a T4. And so our iodinated tyrosines are going to start to link together with one another. And as those come together, that's going to lead us to our T3s and our T4s. Now we've got this T3 and T4 sitting inside the follicle. Now it needs to get out. So we're inside the follicle itself. Here's our follicle. We've got our little follicle cells around there. And we've got a better drawing on the next slide here. We need to get that T3 and T4 back through the follicle cells and into blood vessels nearby. And so now we're going to have to go out, and those cells are going to pinocytose. So we're going to create a little kind of bubble here that contains the components of our T3 and T4. And so now we've got our thyroglobulin moving into a little follicle inside the cell. Now it's inside this follicle cell. All of the pink here is our follicle cell. It's trapped inside and was brought into the inside of the cell. Now it's inside a lysosome. And inside that lysosome, we've again got enzymes, and those enzymes are now going to start to cleave off from our thyroglobulin our T3s and our T4s. So this is going to get us our T3s and our T4s separated from one another. And then they're going to get exocytosed out into the bloodstream. Now they're moving into the tissues there, but they're not going to just travel along all by themselves. They're going to have to be bound up to some proteins. And so we have a thyroxine binding globulin, this TBG here, and that's going to bind up some of our T3 and T4. Some of it's going to be free T3 and T4. And so those will be free floating, but a large majority of it is actually going to be bound to proteins as it floats through the bloodstream itself. And so it's going to make its way through there. So just a little bit different picture. I kind of like this picture better because it shows the thyroglobulin here a little bit better in kind of its true state. So we've got this big long protein here. We've got tyrosines on there. Some of them are T2s. Some of them are, there's another T2 over there. Oh, that's actually a T1 on there. And we're going to start to combine them together and we get T4s and T3s all together. And then that whole thyroglobulin molecule is what's going to get pinocytosed. That then combines with our lysosome. Our lysosome then cleaves off T3s and T4s, and then those T3s and T4s go into the bloodstream. Some of them then bind up to our thyroxine binding globulin, and so that's going to be our protein that helps to carry it along. It helps to limit the amount of degradation of the T3 and T4, helps to limit the amount of loss of T3 and T4 until it actually gets to the tissues where we need it. And then it goes on its way and basically travels to all cells throughout the entire body itself. And so those are going to be in there. The majority of the proteins that we have in the blood are actually produced by the liver. And so our TGB is no exception there. And so our thyroxine binding globulins are produced by the liver. Those are going to go out and bind up the components that are there as well. And that's going to allow us to get them to the tissues, in a sense, kind of safely. The T3, as I said before, is much more biologically active. And so this is what's going to be giving us a better kind of a output from the thyroid itself. But T4, once it gets to the tissues, this can be broken down, in a sense, into and activated into T3 in the tissues themselves. So we're going to convert that T4 over to T3, and then we have something, in a sense, useful at that point. T3 and T4 levels, or thyroid hormone levels, are going to be a negative feedback system, and so it's going to feed back on itself. As thyroid levels go up, then we're going to decrease our production and bring it back down. As thyroid levels come down too low, we're going to bring them back up, and so on. And so we're going to kind of keep it along a level amount there, so we have it within the body itself. But that feedback goes all the way back to the hypothalamus. So if you remember when we were talking about the hypothalamus and we talked about our TRH, our thyrotropin releasing hormone, so we get TRH to TSH to T3, T4. And so that's kind of the process that goes. So if we have a problem with thyroid hormone, either being too little or too much, we may have a problem way back here at the hypothalamus. We may have a problem at the pituitary gland, or the problem may actually be in the thyroid itself. So we need to know what TRH levels and TSH levels are as well. And if we have, say, a high level of thyroid hormone, and at the same time we have low levels of TRH and TSH, we know that the problem is coming from the thyroid, because both of these aren't telling the thyroid to produce the hormone. They're trying to essentially block it. And so they're trying to make it so that we don't make any, yet the thyroid gland is producing lots and lots and lots of thyroid hormone. If it was the, say, TSH that was elevated, so now TSH is elevated, TRH is low, but our thyroid hormone is still high as well, that would mean that our problem is back in the anterior pituitary there, and so we're getting too much TSH production as well. So with the thyroid, it's kind of a mystery in a sense as we go through to look for what is actually happening in the tissues themselves. So which one of those components are actually the problem for our increased or decreased output of thyroid hormone. In addition to producing thyroid hormone, the thyroid gland also produces calcitonin. And so calcitonin is produced by the parafollicular cells. These are also referred to, you'll find them called C cells. These parafollicular cells are going to be producing calcitonin, and calcitonin is going to be the antagonist for parathyroid hormone. So if you remember back to bones, we had two hormones for increasing and decreasing calcium in the blood, and calcitonin and parathyroid hormones were those two hormones. And so if we've got elevated levels of calcium, so we have increased calcium, that means that we're going to want to get rid of that calcium. And so that's going to lead to an increase in calcitonin. And with that increase in calcitonin, we're then going to get a decrease in calcium in the blood. So calcitonin is going to have a target in a couple of different places within the body itself. And so it's going to inhibit osteoclastic activity. And if you remember, osteoclasts in the bone are the cells that actually allow for bone resorption. So this is going to break down the bone. And so this would normally release calcium into the blood, and we don't want that at this point. We don't want any more calcium to be coming into the bloodstream from the bone. So the other side of the process itself that is there is that it stimulates calcium uptake into the bones themselves. And so as it gets it into the bones that's there, then we're going to put it away into the bones and stimulate that component that's there. In terms of the process itself, it's just simply a humoral type of a stimulation. So we're using the actual calcium levels themselves, whether the calcium levels are up or whether those calcium levels are down, to essentially regulate the entire process itself. So since we have calcitonin, that means we're also going to need our parathyroid hormone in order to kind of get the other side of the equation there. And that's what we'll talk about in just a little bit. The thyroid gland, in terms of its function, is essentially there for maintaining body metabolism. So if we're not getting enough thyroid hormone, we're going to have hypothyroidism. And this comes in a few different varieties as far as what can be causing it. That is there. We kind of talked about a little bit about it potentially coming from the pituitary gland, from the hypothalamus as well. But in the end, the mechanisms that are normally stimulated are now going to be decreased in terms of their function. So we're going to have a slow metabolism. With that slow metabolism means that digestion is relatively slow, so a person may develop constipation. Their skin isn't going to turn over very well, so they're going to have less turnover of those cells. We're also going to have a decrease in glandular secretions, and so sweat glands, so skin may end up being dry. We may end up with edema. The cardiovascular system is not functioning the way that it normally should as well. And with that, depending upon the variety of hypothyroid that we have, if we have a deficiency in iodine levels, that means that those follicles that we have aren't able to get rid of the thyroglobulin. And so those follicles are going to start to increase in size, and so they're going to get bigger and bigger and bigger, because essentially there's no iodine inside there. So since we don't have any iodine inside there, but we do have thyroglobulin, we have an increase in that causes those follicles to become higher and higher and higher in terms of their quantity, and so we can't get rid of what's inside there. And so no matter how much TSH we produce, no matter what we try and do to it, if we don't have the iodine, we can't make it. And so the size of those follicles gets larger, and when that happens, we get what we call a goiter. And so we'll see that in a picture in just a moment. If this occurs during pregnancy, we have a problem as well. And so if mom is deficient in thyroid hormone, it's going to basically be stolen from the developing fetus, and we're going to have a problem there at birth. And so since we said that it deals with the production of the nervous system and bone, we're going to see big effects in those two areas. And so we're going to have a relatively short, disproportionate body. We're going to end up with changes in the neurological system itself. And so we're going to have impairment there as well that is going on, which means that you have to supplement mom with thyroid hormone. So she needs to get some thyroid hormone so that she is not taking it from the developing fetus. On the other side of the equation, we have hyperthyroidism. So hyperthyroidism is where we now have too much of the hormone, and it's going to speed everything up. And so in terms of what they have, they're going to have a fast metabolism. They're going to feel hot all the time. Hypothyroid going to feel cold all the time. Hypothyroid potentially going to gain weight. Here we're going to lose weight. And so we're going to have that. May feel like their heart is racing. They may have difficulty sleeping, things like that. When it is Graves' disease, it's thought to be an autoimmune disorder in terms of the process that is affecting the cells themselves and causing them to be overactive. Whereas we get a goiter with hypothyroid, here we get an odd change that occurs called exophthalmos. And so this is where it appears that the eyes are kind of bulging out, and this is from a redistribution of the fat that is there. Since the thyroid is overly active here, one of the ways to deal with that is to destroy some of the active cells. And so radioactive iodine can be given to this person, and that's going to destroy some of those cells as it gets absorbed into the thyroid gland itself. And so here we have an example of a goiter, and here we have an example of exophthalmos. And so we have those two changes there that are occurring within the body itself as a result of either hypo or hyperthyroidism. So I mentioned that in terms of the tissues themselves and control of things like our calcium levels, we have parathyroid glands. And so calcitonin was our other hormone. Now we have parathyroid hormone coming from the parathyroid gland that is going to control calcium in the opposite direction. And so these glands are actually on the posterior aspect of the thyroid. And so there are 4 of them sitting on the back of the thyroid gland, almost sometimes very relatively indistinguishable from the thyroid itself, especially on like a cadaveric tissue itself that is there. Inside, we'll see 2 different kinds of cells that are there, and we have the production of our parathyroid hormone. Parathyroid hormone is going to allow us to now increase calcium inside the blood. So calcitonin was for decreasing that calcium. Parathyroid hormone is for increasing the calcium. So when we have decreased calcium levels in the bloodstream, that's going to lead to parathyroid hormone being released, which is then going to lead to an increase in calcium in the blood itself. And so this is going to now, where we inhibited osteoclastic activity before, now we're going to stimulate it. This is also going to stimulate essentially getting as much calcium to be in the body as well as stay in the body as possible. So we need to make sure that the kidneys are going to resorb as much calcium. We don't lose any in the urine. And at the same time, we want to make sure that the digestive tract is absorbing as much calcium as possible. And if you remember, though, back to the bones as well, vitamin D is essential for that process to occur. So in order to increase it in the gut, we also need vitamin D to be there as well. So as we then get an increase in that calcium level, that's then going to, shouldn't have drawn that so far. That's then going to feed back onto the parathyroid gland to inhibit parathyroid hormone secretion as well. If those levels then go too high up, you had a big meal with the calcium in it, that's then going to be positively stimulating calcitonin. There we go. And so we get our negative feedback loop providing for both parathyroid as well as calcitonin release. And this one here is a much better picture than what I was just drawing there. So hormone levels are going to be based upon whether we have a sufficient amount of calcium or whether we have a decreased amount of calcium in the blood that is there. And so depending upon which way we go, that's going to stimulate either the calcitonin release or that of parathyroid hormone itself. So when we have low levels of calcium, that's going to stimulate the release of that parathyroid hormone, which then brings those levels back up. As calcium levels go back up, that's going to stimulate the release of calcitonin. And then that release of calcitonin is going to bring calcium levels back down. If those go too far, then we're going to end up going back into the need for them to be added a little bit more. And that ends our look at the thyroid gland and parathyroid gland. And next up, we'll continue on into the adrenals.